Because of the problems that we have seen with the lax method, that this is not consistent, the lax method has to satisfy a very precise condition, and it makes this method really expensive and also dangerous because it's not consistent, dangerous to apply computationally. So we have to look for another method where the stability range is wider and not to be so dangerous to apply. And this is called the staggered leapfrog method. And the characteristic of this method is that it's second order accurate both in space and time. And as we'll see, it pushes right to the stability limit with a smaller computational time. That's what we need. And this is actually the final difference representation for this method, because if you remember, when analyzing the partial derivative of u with respect to x, it was actually second order accurate in x. But when analyzing the partial derivative of u with respect to time, we consider just the first order accurate on delta t. So we have to consider a finite difference representation for the partial derivative of u with respect to time to be also second order accurate on delta t. And this is the finite difference representation that we have for that, with the two that in both cases it's simplified actually. And as you can see, they are both actually are the same. The only difference is that where we have here for example, when analyzing the partial derivative of u with respect to x, we have that it's connecting the n plus 1 and n minus 1 points, while when we are doing that for the partial derivative of u with respect to time, we are connecting the j plus 1 and j minus 1 times while keeping the n the same. So one can be obtained actually from the other, where just changing what happens with n, applying it to j. So this is therefore the finite difference representation for this method. Next, as we are doing with the method, with different methods, we are going to analyze the stability of this method. So again, we are going to apply the Fourier or von Neumann stability analysis. As you know, it's very straightforward. So when we are doing that, we have the left, when we are substituting the value of u and j by this eta function to j e times k and delta x. When we are doing that, this is the expression that we have. Again, we have to simplify as much as possible. Again, every time it appears eta to j everywhere, so you have to simplify it. It appears this exponential, so we simplify it again. So this is the expression that we have in this case. As we have here 1 over eta, we multiply everything, all the equation by eta. Just consider again that this is actually 2 times I, the 2 times I sine k delta x. We're doing that substitution. This is the expression we do have. So we bring that to the left. So this is what we have. Again, we have an equation for the eta function, and if we solve that equation for the eta function, this is the results that we have. So once we have that, we have to check what happens with the absolute value of eta. This is a complex number, so again, we do know how to calculate that. So but we can have different possibilities. So we can have this, the square root of this one, to be a complex number as well. So if this one is higher than 1, then it would be a complex number, and in this if this is actually if this is lower than 1, which basically means that if this one is lower than 1, the coefficient of the sign is lower than 1, then this one will be real. If this is a whole complex number, then eta will be always higher than 1. But if this is a real number, then when we're analyzing the modulus, just taking, for example, the square, because the modulus will be the square root of all these things, If you take it the square of that, that will be the case just considering the case of that to be a real number, because if this is not a real number, if this is a complex number, that will be just the opposite of this one. And then in this case, that will have it to be higher than 1. But in this case, what happens is that if this is a real number, so if we are in such a case, in this case, we have that the modulus of eta will be just 1, because this contribution cancel each other. So it would be 1. Therefore, if this condition is satisfied, again, if we do have the current condition, it arises again, then we have that the method is stable. But there is no diffusion here, no diffusion for any delta t and delta x that satisfy this one. There is no diffusion. So here, with the stability range, as you can see here, it's much wider than the one we had for the lax method. And besides that, this method is consistent. That's why there is no diffusion here. And it makes that, considering that the stability range to be wider, it makes the method not so less expensive to be applied, because you can play with both delta t and delta x. You can play with the time step and space steps. So in order to fit your accuracy requirement associated to the problem. So considering a finite difference representation to be second order accuracy both in space and time, we are getting the staggered leapfrog method. And as we have seen here, this method is more stable. It's stable actually if it satisfies the current condition, and consistent as well.